Last time we talked about minimum spanning trees, abbreviated as MST. So let's briefly review what MSTs are. First of all, spanning trees is a connected subgraph. And when we're talking about connected subgraph, we're dealing with undirected graph, where all vertices are connected with the minimum number of edges. So for example, we want to connect all these 5 vertices or nodes with the minimum number of edges. And there were multiple answers to this problem. And an undirected graph can have multiple spanning trees. And after we talked about spanning trees, we talked about minimum spanning trees. And minimum spanning trees is a spanning tree with the minimum possible total edge weight in a weighted undirected graph. So in the previous case, when we were talking about spanning trees, we were interested in undirected graphs. However, in the case of minimum spanning trees, we are dealing with weighted undirected graphs. So the edges have weights, and we want to connect all these nodes or vertices with the edges that end up with the minimum possible total edge weight. And there were 2 algorithms, Cross-Gauss algorithm and Prince algorithm. And in the last lecture, we talked about Cross-Gauss algorithm. And what was Cross-Gauss algorithm? The overall procedure was as follows. We first sort all edges by their weight in the ascending order. So that means we are dealing with the edges with the minimum weight first. And after we sorting all edges, we add edges in that order into the MST. We skip the edges that will produce cycles. And repeat this procedure until n-1 edges are added to our MST. So it was pretty simple. And I gave you one concrete example. We first sorted the edges. And we selected this one first. And after we chose this one, the edge 3 and 5 are connected. And these nodes are included in our MST. And then we chose the next one, this one, as our MST. And vertices 1 and 2 are connected and are in our MST. And after this, we included 2 and 6, this one, and the vertex 6 are now in our MST. And the next one was 0 and 2, which has 31 weight. And now vertex 0 is in our MST. And when we encounter this edge, 1 and 0, we do not include this edge because this one creates a cycle. So we are not including this edge. So in this way, we found our MST. So that was the procedure. And last time, we stopped at 1 pp vector size. So we'll continue on that. So last time I gave you the pseudocode of Cross-Gauss algorithm to check whether adding a new edge creates a cycle or not. We utilized disjoint sets. And using this disjoint set, we could inspect whether certain vertices create cycles or not. So we first sorted the edges in the ascending order. And we inspect each edge 1 by 1. And if these 2 edges, these 2 vertices are not in our MST, we added these 2 vertices in our MST and the edge and calculated the MST cost. So this was the pseudocode. And I gave you this problem at the last, in the end of last lecture. So what we want to do is find the minimum spanning tree using Manhattan distance. So given some points, a set of points, we want to connect all these points with minimum cost. That was our problem. And I explained this example. And to calculate the cost, we need to use Manhattan distance rather than Euclidean distance. And I gave you some hints. First of all, we are going to connect each pair of points with a weighted edge. And then the weight is going to be the Manhattan distance between those points. So given 1, 2, 3, 4, 5 points, we're going to connect all these points with edges. So we're going to create 5 combination 2 edges. That was the first step. And after creating edges, creating n combination 2 edges, the problem now becomes finding the minimum cost or finding the cost of minimum spanning tree in this graph. And we're going to use this edge class to process the edges, and to create a weighted graph, we're going to use this class edge. And after that, to sort the edges in the ascending order, we're going to use heap. So that was our strategy. Okay, so let's solve this problem together. First of all, we need to check some base cases. If we are not given any points or the length of points equals 0, then we just need to return 0 because there's nothing we can do. Otherwise, we are going to retrieve some crucial informations like how many points we have, and we're going to create a priority queue. This one is going to be priority queue. And we are going to create disjoint sets to check the connectivity, or to check whether adding new edges creates cycles or not. And as I explained using the hint 1, we are going to connect each pair of points with a weighted edge. And in doing so, we are going to use this edge class. Okay, so for each point, what we are going to do is like this. We're going to retrieve the point first, and then for every other point, what we are going to do is calculate the distance. So the cost is going to be, we're going to calculate the Manhattan distance, and that is very easy to calculate because we need to calculate the absolute difference between the 0.1 and 0.2 in the x coordinate and y coordinate like this. So this is going to be our Manhattan distance. And we're going to create an edge signifying connecting point I and point J, jth point, with this cost, this Manhattan cost. And we are going to add this edge to our priority queue. So this is the first step, processing or creating a graph using the given points. So this is the first step. And the second step we are going to do is we need to sort the edges in the ascending order. So we're going to heapify the priority queue. And if we just add edges to our list, Python list, it is not prioritized or sorted. However, when we call this function heapify, then this priority queue becomes sorted. So I explained this in the priority queue class. And the next thing we need to do is now run cross-calls algorithm. So this one is sorting edges. This one is creating a graph, weighted graph. So we are taking the third step, cross-calls algorithm. So we are going to calculate the resulting cost. And we are going to count the number of edges we have added. So while priority queue is not empty and count is larger than 0, what we are going to do is from our heap queue or priority queue, we're going to retrieve the first edge and investigate whether this edge creates a cycle or not. How do we do that? What we are going to do is just check whether point 1, point 2 are connected or not. If they are not connected, then that means we can add this edge to our minimum spanning tree. To do so, we're going to connect these 2 points using our edge. And we're going to add the cost. And we're going to decrement the count. So we are repeating this process until we retrieve n edges, n-1 edges. And we're going to return the results. So this is the end of the solution. Any questions up to this point? Okay, this is how we apply cross-calls algorithm to solve this problem. Okay, let's move on. So up to this point, we talked about cross-calls algorithm, and I told you that there is another algorithm to find the minimal spanning tree, that is Prim's algorithm. So what is a Prim's algorithm? Let's see the overall procedure first, and then have a look at a concrete example. First of all, we're going to initialize the minimal spanning tree with a vertex chosen at random. In the case of cross-calls algorithm, we started with the minimum weight edge. However, in the case of Prim's algorithm, you can start at any random vertex. That is the difference. And the next thing we're going to do is find all the edges that connect the tree to new vertices. So we are inspecting all the edges connected to this vertex and find the minimum and add it to the tree. So this description might sound somewhat ambiguous. And we're going to keep repeating step 2 until we get a minimum spanning tree. We're going to repeat this process n times. I'll give you a concrete example. So first of all, we're going to have, first of all, we need to create this table. This column signifies the IDs of vertex, and key actually means cost to reach this node. And parent node is going to be the vertex that is connected to this vertex to have this cost, this minimum cost. And let's say we choose vertex 0 as our starting point. Then because we are starting from vertex 0, this one will have cost 0. And because we are not connecting this node with any other node, its parent stays none. That is the first step. And the next step is because this node is connected to vertex 1, vertex 2, vertex 5, and vertex 6. So we are going to inspect these 4 nodes, these 4 vertices, and update the cost and its parent. So when we are connecting vertex 1 through parent 0, its cost is going to be 32. So its cost is going to be 32. And vertex 2, when it is connected through vertex 0, its cost is going to be 31. So it means this connection. In the same way, vertices 5 and 6 are going to have these new costs. And after we inspect all the edges connected to vertex 0, we mark vertex 0 as done. So here, actually, we need to have one more column. Processed is true or done. Okay. And then what we do is, other than the processed vertices, we're going to choose. So among these vertices, we are going to choose the vertex with the minimum cost. So that's going to be the vertex 2. So now we are in the process of processing vertex 2. Now we need to inspect all the edges connected to vertex 2. However, vertex 0 is already processed, so we are not considering this edge. And when we do this, the cost to vertex 1 was originally 32 when it was connected through vertex 0. However, if we use vertex 2 to be connected to vertex 1, the cost is smaller, 21. So we need to inspect vertex 1, 4, and 6 and update the cost as follows. So if we connect to vertex 1 through vertex 2, then we can have better cost. So it's going to be 21. And in the case vertex 4, the scenario is similar. It's better than using vertex 0, but it's better to vertex 2. So its weight is now 46. Similarly, we update the key of vertex 6 as 25 because connecting to vertex 6 through 2 is better than connecting to 6 through the vertex 0. And after we are done with vertex 2, we mark this column, row, as done. So from now on, we are not considering vertex 0 and vertex 2 because they are already processed. We are done with processing vertex 1, vertex 0, and vertex 2. And can you figure out the table after we execute all the process of Prim's algorithm? I'll give you like 3 minutes and try to find out the table after Prim's algorithm. And as usual, if you have any questions, you can ask now. I'll give you 3 minutes. I'll give it 30 more seconds. Okay. So this is the end result of the table after we execute all the process of Prim's algorithm. So as you can see here, we are connecting vertex 1 through vertex 2. So that is going to be this edge. And vertex 2 is connected through vertex 0. So it's going to be this edge, this one. And vertex 3 is connected through vertex 4. So it's going to be this edge. Vertex 4 is connected to vertex 2 with this edge. And vertex 5 is connected to vertex 3. And vertex 6 is connected to vertex 2. So this is going to be the minimum spanning tree we found with Prim's algorithm. And before we move on, one thing to note is this minimal spanning tree is the same as what we found using Kruskal's algorithm. So basically, we found 0, 2, 3, 5, 3, 4, 2, 4, 1, 2, and 2, 6. So basically, this is same as Prim's algorithm's results. And Kruskal's algorithm and Prim's algorithm produce the same result, however, with different computational efficiency. And for so I told you that when you are using Prim's algorithm, you can start at any random vertex, and it doesn't really matter where you start. It will always produce the same result. And you can, in fact, prove that Prim's algorithm produces the same result wherever you start. However, that's the out of scope of this course. And you can learn that in the algorithms course. So that is one note I want to make here. And let's implement Prim's algorithm. Okay. So let's see Prim's algorithm. So as usual, I'll just give you the pseudocode rather than the full implementation. Let's say G is the graph and S is the starting vertex. And here key was the weight, and PI is the parent of vertex I in MST. And visited is whether vertex I is visited or not. And here, let's say n is the number of vertices, and key pi visited is going to be initialized like this. The parent of vertex I is initially none, and visited or processed is false at first. And we can define this inf as a very large number, like 1 to the power of 10 to the power of 100, like this. So we can make this number very big. And what we are going to do is we are going to mark the starting point the weight of the starting point as 0. So we are initializing. The starting point, the weight of the starting point is 0. And what we are going to do is we need to repeat this process n times as and n is the number of vertices. First of all, we need to find the mean index. So here, what we are doing is, when we are starting from here, we want to find the minimum edge that is connected to the current node. Okay, so that is why we are doing this loop, finding the minimum weight connected to the current node. So we are finding the minimum weight among not visited. So if not visited, and you need to find the key. And if this key is smaller than the mean key, then mean index, the mean key, going to be I and key I. We are using this for loop because we want to find the index of the mean key and mean value. And after this, we are going to make visited mean index as true. And at this starting point, other values are infinite. However, only the starting point has the weight 0. So at first loop, the starting point will be chosen. And after this, we're going to inspect neighbors of the current vertex. So for V and VA in G, and I told you that let's assume that this one returns the vertices connected to this mean index vertex. And if not visited, and this value is smaller than the weight we have in our table, then we're going to update the value or the weight and the parent as mean index, like this. So this is basically what Prim's algorithm is about. So any questions regarding this implementation? So this is what we are doing after we choose the current vertex. I made a mistake in explaining this part. Okay. Any questions regarding Prim's algorithm? Well, let's move on. So figuratively, let's compare Kruskal's algorithm and Prim's algorithm. So in the case of Prim's algorithm, we are expanding the MST by starting from a random node. However, in the case of cross-call algorithm, we're just starting from, let's say this one is decentralized. So we are connecting small graphs and merge these small graphs step by step. And in the end, we're going to create the same MST as Prim's algorithm. Okay. More technically, I told you that cross-call algorithm starts from the minimum edge, whereas Prim's algorithm starts from any vertex. And we inspect one node only once, because we are starting from the minimum edge. However, in the case of Prim's algorithm, because we have two loops, we could inspect one node more than one time. And the time complexity of cross-call algorithm is O E times log V. Here E is the number of edges, and V is the number of vertices. Okay. In the case of Prim's algorithm, what we implemented has the time complexity of OV square. However, in the advanced course, you are going to learn how you can reduce this V square to E plus log V. So in the case where the graphs are sparse, suppose they have the same number of V, but different number of edges. And if E is smaller than V, then we say the graph is sparse. So cross-call algorithm is faster when the graph we are dealing with at the moment is sparse. However, in the case of Prim's algorithm, it is faster if the graphs are dense, meaning that E and V have similar values. So you need to choose which one to use according to the characteristics of the graphs you are processing at the moment. Okay, that was about minimal spanning trees. And from now on, we're going to talk about shortest path. Previously, we used the BFS to find the shortest path. However, the BFS algorithm can only solve the shortest path problem in unweighted graphs. But in real life, we often need to find the shortest path in a weighted graph. For example, there may be many routes from your home to a target location like school, and the time needed for each route may be different. The route with the shortest distance may not be the one with the least time because of the speed limit and traffic jams. So, for example, when you want to go to Seoul from Gwangju, if you drive on your own, then it could take 5 hours. However, let's say if you drive, you just need to drive 400 kilometers. However, if you take SRT, then it takes only 2 hours, and the distance is 600 kilometers. Let's just assume. In this case, what we are interested in might not be the distance, the actual distance, but the time we need to spend. So anyway, because we need to think about the weight, and BFS can only deal with unweighted graphs. However, in real life, we need to think about weighted graphs. We better come up with better algorithms. And that's why we are interested in Dijkstra's algorithm. And there are 2 or 3 algorithms. The first one is Dijkstra's algorithm for a weighted directed graph with non-negative weights. And we have Bellman-Ford algorithm for graphs with negative weights. And the basic version of Bellman-Ford algorithm deals with graphs with no negative weight cycles. An improved version provides enhanced high complexity. So basically we have 2 or 3 algorithms. However, in this course, we're going to talk about only Dijkstra's algorithm, and we're not going to discuss Bellman-Ford algorithm. This, you will learn this in the next course. Before we talk about Dijkstra's algorithm, some students might be confused at this moment. So what is the difference between minimum spanning tree and shortest path? They look similar. In fact, they are similar. In the case of minimum spanning tree, the purpose is connect all vertices with minimum weight. However, in the case of shortest path, we are specifically interested in one starting point and one target point. So we are given the starting point and the target point, and we want to find the minimum weight reaching target from this starting point. So this is the difference. So in the case of minimum spanning tree, we're connecting all vertices. So we want to visit all vertices. However, in the case of shortest path, we want to reach target from the starting point with the minimum cost. So that is the difference. Okay. All right. From now on, let's talk about Dijkstra's algorithm. Dijkstra's algorithm for a weighted directed graph. However, we need to assume that the graphs do not include negative weights. So all the weights should be non-negative. And what we are going to do is we're going to create a set P, which contains the shortest path tree set. So we're going to add an edge 1 by 1. And through this, we can keep track of vertices, including the shortest path tree, whose minimum distance from the source is calculated. And we're going to assign a distance value to all vertices in the input graph. So we're going to initialize all distance values as infinite. So in the previous slide, I told you that we want to find the minimum, the shortest path between the target and starting point. However, in practice, we just find the shortest path from the starting point to all nodes. So this is the ideal case. In practice, we find the shortest path from the source to all other vertices. So that's what we do. While P doesn't include all vertices, we are going to pick a vertex U not in P, which has a minimum distance value, and we are going to add U to P and update distance values of all adjacent vertices of U. And to update the distance values, we're going to iterate through all adjacent vertices. And when you look at this description, this one is quite similar to Kruskal's algorithm. Indeed, it is quite similar. And for every adjacent vertex V, Prim's algorithm, if the sum of distance value of U from source and weight of H, U, and V is less than the distance value of V, then we're going to update distance value of V. So this is very similar to Prim's algorithm, starting from a random vertex and update all the weight to reach that vertex. However, in the case of Dijkstra's algorithm, we are not starting from a random vertex, but we are starting from a specific vertex given. So we are going to have three types of vertices: processed one or current one, and the vertices we need to update. So let's say we are starting from vertex 1 and calculate the distance to all the other vertices. And here P means parent. So Dijkstra's algorithm for a weighted directed graph with non-negative weights. We're starting from vertex 1, and the distance to vertex 1 is 0 because we are starting from vertex 1. And we need to update the distance to vertex 2 and 3 because they are connected to vertex 1. So at this moment, this one is the current vertex, and these two vertices are what we are trying to update. And to reach vertex 2 through vertex 1, the cost is going to be 3. And to reach vertex 3 through vertex 1, the cost is going to be 5. And next, this one is now processed, and the current vertex is going to be 2 because it has the minimum weight among unprocessed vertices. And at this moment, these two vertices are going to be the ones that needs to be updated. So in this case, when we try to reach vertex 3, if you reach vertex 3 through vertex 1, the weight was originally 5. However, if we try to get to vertex 3 through vertex 2, what is the cost? The cost is going to be 1 plus 3. So cost to vertex 2, 3, plus the cost of vertex 2 and 3 is going to be 1. So we have found better cost, which is 4. So we're going to update it as 4. And to reach vertex 4, it's going to be 3 plus 6. This is the cost between vertex 2 and 4. And this is the cost between vertex 1 and 2. So that's how we update these nodes. And can you figure out the table after we execute all the process of Dijkstra's algorithm? I'll give you 3 minutes and try to complete this table. I'll give it 30 more seconds. Okay, let's check the answer together. So this is the complete result. This is the result when we completed the Dijkstra's algorithm. Any questions regarding this result? Okay, let's move on. So we are going to implement Dijkstra's algorithm here. The Dijkstra's algorithm. We're given graph G and the starting point S. Here G is the graph we are given. S is going to be the starting point. And we are going to create D and P. And B stores the minimum distance from S. And P stores parent to recover a path, shortest path. So we're going to create DP visited like this. And D is at first, contains very large numbers. And here N is the number of vertices times N and false times N like this. And we're going to initialize the distance of the starting point as 0 like this. And we're going to repeat this process for N times, and we're going to find the mean index and mean value. So we're going to initialize this one as -1 and very large number. And for every other vertices, we need to inspect which is the smallest distance vertex at the moment. So this part is very similar to that of Prim's algorithm. And after we found the vertex with the minimum cost among not visited vertices, we are going to update the visited status as follows. And what we are going to do is, for the neighbor of this node, what we are going to do is, if this vertex is not visited, and the distance to this vertex is smaller than this new value, and we're going to update the distance and parent as this new value. Like this. So this is basically the implementation of Dijkstra. All right. So today, we talked about minimal spanning trees, basically Cross-Gauss algorithm and Prim's algorithm. And in the case of minimum spanning trees, we try to find the way to connect all edges. However, in the case of shortest path, we wanted to find the minimum distance from a specific vertex to every other node. Okay.